Case 2, pay attention. At a point on a line perpendicular to the rod, all right? So you have a rod AB, the same rod, okay? But this time the orientation I've kept vertical. Why? For a better visualization, nothing else. I can tilt the diagram 90 degrees. That's not a problem, okay? This is just for simplicity. So you have a rod AB whose linear charge density is lambda, whose length is not defined in this case right now. I'll tell you why. You could have defined, okay? I'm just keeping the number of variables to minimum. You could have defined. A point P is R away from the rod. This is a randomly located point P, okay? Deliberately the diagram is drawn in such a way. So what is the modus operandi? I'll take an element, sir, of length dx. I'll define its charge dq, which will be equal to what? Lambda dx. Then I will join that lambda dx or dq with a straight line to my desired point. Look at the diagram, right? That dq element of yours and length I have taken dy. Lambda dy gives me dq. Straight line joining the point P is by Pythagoras theorem under root y square plus r square. What is the value of dE at point P? K dq upon y square. K, who plays dq? Lambda dy upon r square. In this case, r square, when I say r square, I mean the formula r square. In this case, who plays r square? Under root y square plus r square whole square. So the radical gets killed by the square. You have k lambda dy upon y square plus r square. Fine, sir. We got it. Now what? Let's add them all. Let's add them all. But now as you traverse the rod, all the DEs are in different direction. You cannot add them like numbers. So divide and rule. Break the vector down into its two components, right? Before I go ahead and do that, I'm trying to highlight what is the method of substitution I'll be looking for. And it's not that I need to guess that. It's right there available. But question, why do we need to do that, sir? Okay. Look at the expression for DE. Do you have a y there? Right? Do you have a y square plus r square in the denominator? Yes. Having a complex integration is the last thing you want. We avoided last time by taking x as a distance. Here we could not. So what do? Always go for angular substitutions. Polar integrals, mark my words, polar integrals or trigonometric integrals are always, I rarely use that word, are always easier to handle as compared to algebraic integrals. Always. Okay? Because they simplify the expression. So, y equals r tan theta, clearly. dy will be equal to r secant square theta d theta. What did I do? I differentiated both sides with respect to what? With respect to theta, y, whatever. Right? Depending on which variable you want. Because then cross multiplication will take care of it. Okay? Or sometimes when they skip a step and they don't write the denominator, you know what it's called? Maybe if you come across in some other book. This is called taking differentials sometimes. So if somebody says taking differentials both sides, don't get taken aback. It's the same thing. Okay? Alright. Divide and rule. This angle is theta. So because it's a vertically opposite angle, this angle is also theta. DE gets broken down into DE cos theta. See, by default, horizontal I chose as x-axis. It's your go-to response. It's your inner conditioning now. Okay? DEY equals DE sin theta. So, sir, what's the agenda? We will integrate all the x components separately and y components separately? Yes, we will. But, sir, that will be a long process. So, let the process be long. The result will be very small. And if you want to remember the result well, derive it. If you know where it's coming from, you will never forget it. Alright. So, let's address the x component first. You can see asymmetrically located point P, the angle is theta 1 and theta 2 deliberately to give you a general case. Okay? dy is r tan theta and dy is r sec square theta d theta. All set, and dex is my component which is normal to the rod. Alright. Then dex, I put the value k lambda dy cos theta. De expression was already there. I put a cos theta to it. Now is the time to make sure everything is in terms of theta. Okay? Put the value and see what happens. Instead of dy, you put r secant square theta d theta, right? And lambda stands as it. r is as it is, and bottom, instead of y square, you put r square tan square theta. Note r square can be taken out common. 1 plus tan square theta is sec square theta. How convenient. Life is great. Sec square theta in the numerator cancels with the sec square theta in denominator, and you are left with what? K lambda by r cos theta t theta. How simple is this expression as compared to a y square plus x square? Isn't it? Okay. Are all the x components in same direction? Yes, sir. Integrate. K lambda by r comes out of the integral sign. What's inside is integral cos theta. Hold on. Two extremely important things. One I will tell you right now, and the other one I will tell you in the final result. Integration limits will be minus theta 2 to plus theta 1. Why? Because you have to respect the fact that your baseline is the line P. Anything below and anything above have to be given different signs to respect the fact that they are on opposite side of the reference line. That's why minus theta 2 to plus theta 1. Alright? Integration of cos theta is sine theta, upper limit minus lower limit. Sine theta 1 minus sine minus theta 2. And sine is an odd function, so inside minus comes out. That minus nullifies the in-between minus, and you have a beautiful expression K lambda by r sine theta 1 plus sine theta 2.